A few weeks ago I built this dedicated workstation out of my old PC and a 3D printed and aluminium case. This is an all-in-one transportable computer which basically is running Ubuntu 18.04 with ROS on it, the robot operating system. That makes my life a lot easier than running on a VM on Windows 10, which is what I was doing before. In this video we're going to do the same thing, but with my everything remote, as I named it, and this remote control I've had kicking around since OpenDog version 1. I use it to control all my robot projects. It's just an Arduino Mega and an NRF24L01 chip that talks directly to the robot. It's got two 3-axis joysticks and a bunch of toggle switches and an LCD that doesn't display any useful information. So when I'm driving a ROS robot around manually, doing mapping perhaps, I have to use a keyboard to steer at the moment using the keyboard teleop program. Now ROS is a network operating system, so what we really need to do to make a remote to drive the robot instead is put a single board computer in. Now it'd be really good to have a touch screen as well, so we can assign as many buttons and things we want on an interface, although it's still good to have some physical switches. So let's have a look at the parts. We're going to get printing and see what's inside. Most of the parts are printed for this project, but before we have a closer look at those, thanks to 3D Fuel for the filament for this project. Don't forget to check out my channel for more 3D printing projects and check out 3dfuel.com. So we've got this box with a big hole in and a lid on the bottom that screws on, and we've got these lids as well for these little boxes on the side. It's a bit like a Nintendo Switch, other than these are going to be fixed on permanently. Obviously I've got two 3-axis joysticks here. We've got these buttons which are a bit like the menu buttons and the select button on my existing remote. And this side, where I'd normally have the motor enable, I've just got a big emergency stop switch. I mentioned putting a touchscreen in so we can configure different interfaces. So this is the Raspberry Pi official 7-inch touchscreen, and on the back I've already mounted a Raspberry Pi 4. Now that's the monitor cable that goes off to the display, so you don't use the HDMI sockets up, and these are the cables which are I2C that go to the GPIO pin, and that's for the touchscreen. I've bolted these sections together and I left bolt holes to just put a nut and bolt in, and obviously we've got to do some wiring for the joysticks and buttons eventually. And my screen and Raspberry Pi should neatly drop in like that, and I've left a hole here so we can get to the ports of the Raspberry Pi if we need to. Now obviously the monitor's connected anyway with that cable, so we don't really need to plug anything apart from power in, although we could get to those extra HDMIs if we need to. The only things we can't get to are USB, which are on the back here, but I've got a plan for that, which we'll look at later. There are several approaches we could take to getting the data in from the joysticks and the buttons and sending those as messages over the network to other ROS nodes. Now ROS itself is basically network enabled, so we have a ROS core that runs somewhere. It could all run on the same machine, but in my case it's probably going to run on this workstation. And ROS core is a bit like a directory where nodes can register so they can find each other, they connect with topics and send messages over those topics. So we could go and get the analog joysticks and the buttons into the Raspberry Pi. Now the Raspberry Pi doesn't have any analog ins, so we'd need some sort of extra interface that turns that into serial. Perhaps we could build something with an Arduino or find an I2C chip with lots of analog ins or something like that. Then we can write a script on the Raspberry Pi which will go and take those and turn them into ROS messages. In our case it will be a twist message sent over the command velocity topic for the sticks and something else for the buttons. What I'm actually going to do though is use the Arduino ROS library, the ROS serial library, and I use that in my really useful robot to connect the Arduino that deals with the motor control. So we run up a ROS node on our single board computer, in this case a Raspberry Pi. We can connect with the USB serial to an Arduino, and then we can basically have that Arduino publish the messages, so that would read the analog ins, that would actually broadcast the message over serial to our single board computer, in this case a Raspberry Pi, and that would relay the message on to wherever it needs to go, or at least publish that topic that things can subscribe to. Now the Raspberry Pi itself has got this touchscreen, so that's going to have other interfaces, so that can still publish its own messages, and it could also subscribe to the messages from the joysticks if we actually wanted to display that data on the screen or display the button state, for instance, or anything like that. And we can also get data back to display on here from the robots, as long as that robot publishes its message over a ROS topic we can subscribe to on the remote. I fitted my touchscreen in with these plates either side that screw onto the box, and they screw onto the mounting points on the touchscreen. So what we've got attached to this now is a Teensy 3.2. This is an Arduino compatible microcontroller with lots of I/O that we can use to read all of the buttons and those analog joysticks. On the back of my proto board is a piece of header strip, and that allows the board to neatly mount onto the GPIO header of the Raspberry Pi. Now it's not actually connected to that, I'm not going to use those connections, it's just to mount it, and that's because it's connected with USB, so that makes a USB serial port, and we're going to run the ROS serial Arduino library and the code on here, and then connect over ROS serial to the ROS serial node running on the Raspberry Pi, and that means we can publish those messages straight off the Arduino over serial, and then use the ROS serial node on the Pi to publish those over the network. Right, we're all wired in so that we've got the analogues from those sticks wired into the 6 analog ins on the Teensy, and we've got the 4 digitals going to my 4 digital switches, and that includes that emergency stop switch. I've just written some Arduino code to read those analog joysticks and the digital switches, and for now that Teensy's plugged in with USB to my computer, and we can look at the serial terminal on the Arduino IDE, so we're not using the Raspberry Pi yet. Now these joysticks are pretty cheap, they cost about £10, and they've got kind of this spot in the middle where the spring doesn't center the joystick properly, so we get kind of this place where the value can just vary as you wave the thing around. So as well as having read in the analog ins and all the digitals, I've also made this little function that takes out any values that are in between 50 and minus 50, replaces them with 0, and then takes off 50 from the resulting values so that we still start at 0, but we just get rid of that dead spot. So I'm just reading those out and putting those out to the serial terminal. So now we can see that we don't have a nasty kind of wobbly value in the middle there, but if I turn it, it still starts at 0, and all of those values we can see there for the analog and digital, and the other ones are for the digital switches, which are just 4 digital switches. So that's all very well and good, but what we need to do now is link it to the Raspberry Pi that's in here and use the ROS Arduino serial library so that we can publish that data on the ROS serial node running on the Pi over the network and control ROS robots. So I've written some code which I'm not going to go into in too much detail, although it is open source, and I'll be putting all this code on GitHub as well as the CAD for this if you want to build one. And that code basically does just that. It scales the values down because we don't want to be driving at 500 meters a second. Generally 1 meter a second will do, so we need a float from 0 to 1 meter a second, and probably the same for yaw as well for rotating the robot. Again, we need sort of 1 or 2 radians a second, and that's about it really. When a robot's doing mapping, we don't want to be driving really fast. 1 meter a second is probably too fast, in fact. And that's why it's so good to have those analog sticks. So it takes those values and it publishes a command velocity topic with a twist message. Now I'm going to publish the Arduino library as well that I've hacked, which works with all Teensys, and I had to hack that for my really useful robot, and I've also increased the buffer size so it can in fact send that message over the ROS serial to the ROS serial node running on the Pi. We probably are going to need keyboard access and also a mouse. We've got a trackpad on this one, so I've plugged my wireless keyboard dongle in. That can just stay inside, and then we don't need to worry about the USB ports. I've launched the ROS serial node on the Raspberry Pi here, so that's publishing my command velocity topic, and I've got the ROS core running on my ROS workstation we built a few weeks ago. So we should see now that if we move these sticks around and doing a ROS topic echo for command velocity, we should be able to see those values changing for both the translation and the rotation axis. We should probably try driving a ROS-enabled robot with this now, but before we have a go at that, it's time for a quick ad from the video's sponsor, and that is Arduino, who are providing the building blocks for innovators to power connected experiences for the future with the Opla IoT Kit, and I've got one just here. The Arduino Opla IoT Kit allows anyone to build Internet of Things devices and manage and control them from multiple interfaces such as the Opla hardware device itself, custom web dashboards, or the app which is available for iOS and Android. This functionality has been made possible by combining a wide variety of electronic boards, easy-to-use tools, a collaborative community, and practical project examples to suit all levels. The Opla IoT Kit allows you to add connectivity to devices around the home or office and build your own IoT-enabled projects. In the box is the Opla IoT device itself, and piggybacked on the back of that is the provided MKR Wi-Fi 1010 board. The Opla device fits into this plastic housing that's been provided, and there's 3 screws in a bag to screw it in, and that means its display will shine out through the front. There's also a back here to wall mount it, which clips on, so you can make an IoT device and put it anywhere in your home. It comes complete with a set of 8 Internet of Things self-assembly projects ready to show you how to turn everyday appliances into smart appliances. You can start with no soldering, so it's really good for beginners, but the Arduino Opla IoT kit is also a really good resource for more experienced users too. The kit's compatible with Amazon Alexa, so you can expand your existing home automation, and it comes with a 12-month subscription to the Arduino Create MKR plan with premium access to the Arduino IoT Cloud. You can get it now for €99, and I'll put that link in the description to this video. Right, now let's check this remote out and get a XRobot out. So let's drive the robot with this. Obviously we've got that yaw control, which is on my left-hand stick when I rotate it, which is the same as robot dogs. And then the other stick is for driving, so that is going to be so much easier for doing mapping at least than driving with keys, which tends to sort of turn it on and off. You don't get any analog control really with the default keyboard teleop program. So this is really smooth, and I can drive much slower and rotate as I go, or I can punch it and shoot off to where I want. You want to be quite careful when you're doing mapping, of course, because it needs to look around with the laser scanner and build a map of the entire area. But this is worlds away from driving with keyboard teleop, so that's extremely good. Bit of a lump in the carpet there. And there's no filtering on this really at the moment. It's just driving the wheels the speeds I say, so if I stop dead, then it still stops dead, so I have to be a bit careful. We could put some filtering on. But for now I'm pretty happy with that. I think that's going to be pretty good, and it's going to make my ROS life a lot easier. At the moment, ROS Core is running on this workstation, but it doesn't have to, of course. It could run anywhere. It could run on the remote, or it could run on the robot for that matter. So that means we could just drive this around and not have the workstation, as long as we've got Wi-Fi access points somewhere, but that could be a sort of 3G router in my pocket, or it could be actually an ad hoc network running between the two. But we do need these other functions implemented, the switches, and hopefully something on the touchscreen, so we can control other features of not only that robot, but robot dogs, and all sorts of other robots that I might want. What I've done with the buttons, of which there are 4, is actually used one topic with one piece of data in, and that's an integer. And basically I've assigned each button a value that adds onto that integer, which are basically 1, 2, 4, and 8. So you can see on the remote workstation now, if we look at that topic called buttons, and you can actually see that published on the Raspberry Pi screen as a 16-bit integer, if we press those buttons, we should see that that data goes up, and finally 8, and then we can obviously strip those bits out on any of the robots we want to control to find out which button it is that's been pressed. We could use the 1, 2, 3 and 4, but obviously 1, 2, 4 and 8 are individual bits in that variable, so we could just strip the bits out and then we'd have the data straight away. Typically I use those buttons on the legacy remote to drive a menu up and down through the options, and then press select to select the option, and that puts the robot dog into different modes like walking mode or kinematic demo mode, or initializing the motors and all of the setup. I've also got my motor enable and disable switch on the other side, which I've replaced with that big red button on the new remote. So that's all very well and good for robots that just need a simple menu with several options, but actually in the future I want to use this remote for any robot, so it could need all sorts of settings and all sorts of other functionality, and that's why the touchscreen is so useful, because we can draw any type of display that we want and make embedded menus and settings and all sorts of graphical options, and even get data back like a webcam view and anything else we want to display on there with a ROS message. So for now I don't have much to control, but I've written a proof of concept in Python that uses the ROS.py library, and I'm also using Pygame, which is actually for writing games, but it's really good for doing simple graphics, drawing rectangles on the screen and putting text on the screen, and I'm using that to make the touchscreen work. So basically it works just like a mouse, and when you click, in fact you don't get a mouse button down action anymore in Pygame, but Pygame supports touchscreens, so there's finger up and finger down for touchscreens. So I've written a very simple script that displays a few buttons, one makes it quit, and the other two send some strings which are ROS messages. I'm running that touchscreen script on my remote, and I'm running the ROS core again on my workstation so we can see those messages over the network. So if we do a ROS topic list, we should be able to see that, in fact, as well as the standard ones that come up when ROS Core launches, we can see one called touchscreen. And if we go and look at that topic, we should see that if I click on hello, it should echo hello as a message on that touchscreen topic, and the same with goodbye. So that's just a really simple proof of concept at the moment that notices where I'm touching on the screen, and we can define any coordinates. So we could have a big graphical picture and we could click on different pieces of the robot, for instance, to activate different functions. They don't need to be square rectangles, but that's a proof of concept for now, and that seems to be working pretty well. And of course we can subscribe to ROS topics and display those on the screen in our GUI as well. So we could have the robot publishing its battery voltage as a ROS message and then subscribe to that topic and display that on the screen. And typically with the menu options, the remote acts like a dumb terminal. So as we scroll up and down with these physical buttons, or we use the touch screen to set menu options, those menu options will be kept by the robot, and it would then publish back the menu state we can display on the screen. That means if the remote gets rebooted, when we reconnect, the robot's still kept its mode, and that information's displayed straight back on the screen. So there's still quite a lot more building out to do as I develop the robot, so don't forget to subscribe to check out the really useful robot and the robot dogs and how I integrate ROS and how I integrate this remote and build that GUI out. The finishing touches on this are that it's completely wireless now. So I've put a 20 amp hour USB-C power delivery spec USB pack on its back, and that powers the Raspberry Pi, and it should do for many, many hours. I've also put this stand on so that it can sit up and I can use it like a terminal if I need to type on the keyboard. But of course we can SSH into it as well, so that'll make things much easier if we have to do anything too complicated. That's the end of this video. This project is entirely open source, and I'll be publishing the CAD for this and also the code so far, that proof of concept code and the code that operates all the buttons and publishes all the ROS topics. All of that will be published on GitHub. My really useful robot and OpenDog version 2 are also open source, and as those projects proceed, you'll see this getting developed as well as the robots, and all that stuff will be published. So if you'd like to support me through Patreon or YouTube channel membership, those links are in the description below. Alright, that's all for now.